So in this problem, we're simplifying the radical expression that's given to us here, the cubed root of the expression 40 times t to the 8th times w to the 3rd. We're also told that all the variables here represent positive real numbers, which really doesn't matter to us too much in this problem, but suffice to say, it allows us to avoid having to use absolute value signs in any case. So let's not worry about it here. We just want to simplify this expression as completely as possible. How are we going to do it? We're going to use the same strategy that we employed when we simplified the square root of a whole number. We just need to look underneath that radical and figure out what that expression is made of. What are all of its factors? And once we know what all of its factors are, we'll know how to bring some of those factors outside the radical and therefore make it simpler. So it's the same as before. There's actually, though, one important difference. Besides the fact that we also have variables now underneath the radical, the other big difference between this problem and the last problem is that the index of our radical is different. It's a cubed root instead of a square root, and we'll see how that shows up in just a moment. But so we're going to do kind of a lot of work that's going to look a little nasty here, but at the end of the day, we want to figure out if there's a shortcut, specifically a shortcut for how to deal with variables underneath radicals. How do we deal with the exponents on that t and that w here if we're going to take the cubed root of that expression? So at the end of the day, we're going to also come up with a shortcut. But the strategy is still the same because we're doing the same process. We're simplifying a radical. So the first thing we'll do is to factor the radicand completely into primes. The second thing we're going to do is look underneath the radical. And in the last example, we saw when we were simplifying a square root that if there was a pair on the inside, we could make it into 1 on the outside. But this is the place where we're going to depart from that strategy just a little bit because our radical has a different index. Here it's a cubed root instead of a square root. And so instead of needing a pair on the inside to bring 1 on the outside, for a cubed root, we need to have a triplet on the inside in order to bring 1 onto the outside. So in this example, because we're using a cubed root instead of a square root, we're going to look for groups of 3 of common prime factors or variable factors underneath the radical that we can turn into 1 factor on the outside of the radical. Then if there's any simplification to do, we'll remultiply out all the factors that survive. So let's start by factoring completely. Let's find out what this expression is made of. 40 times t to the 8th times w to the 3rd. We'll use a factor tree again, starting with the coefficient 40, which factors into 2 times 20, and 20 is 2 times 10, and 10 is 2 times 5. So we know 40 is 2 times 2 times 2 times 5. Then we have the variable portions of this monomial, t to the 8th times w to the 3rd. T to the 8th is nothing more than t multiplied by itself 8 times. So if we were to break it apart in a factor tree, we'd just get a bunch of t's, 8 of them to be specific. Same thing with w to the 3rd, we would just get a triplet of w's. So if I wanted to be really brutal about the expression underneath this radical, I would write it as 2 times 2 times 2 times 5 times t 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 times w times w times w. Now we know all of its pieces. And now we can employ the simplifying strategy. Because I'm taking a cube root, any factor which I have 3 of underneath the radical can become a single one on the outside, because the job of a cubed root is to undo the process of cubing a number, or cubing a quantity, multiplying it by itself with a total of 3 factors. So if I find 3 on the inside, I can turn it instead into 1 on the outside. So let's go looking for triplets. First triplet I find here is a triplet of 2's, 2 times 2 times 2. So I can bring that triplet of 2's to the outside of the radical and make it into a single 2. I also find a triplet of t's. I can bring that triplet of t's to be 1 t on the outside. But if I keep looking, I can find a second triplet of t's. Bring those t's on the outside as a single t. And I also find a triplet of w's. So in total, if I do all that bringing out process, I'm going to get a 2 on the outside. I'm going to get a couple of t's on the outside. I'm going to get a single factor of w on the outside of my radical. Then I have a bunch of stuff left over underneath the radical. I've got a 5 and I've got a couple of t's that we weren't able to do anything with. So those get to stay underneath the cube root. Let me just make sure that that typo doesn't get preserved for the record. There we go. So that's a cube root. Okay, great. So now we did all the hard part, the simplify part. Now we just have to remultiply everything back together and write it in a slightly simpler fashion. And really that just means taking the t times t's that we see here and just rewriting them in the slightly easier on the i's version, t squared. So our final answer here is going to be 2t squared times w times the, again, cube root of 5t squared. Well, okay, great. Except that this was kind of a nasty, really long-winded way of going about this problem. What's the shortcut? What's the guiding principle that can help us do this without having to write out all the factors of t the way that we did here and all the factors of w the way that we did here? What if you were given square root of t to the 150th power? I certainly wouldn't want you sitting there and writing out 150 t's, factors of t, on your paper. It's just a waste of time after a certain point. So hopefully we have an understanding of how a shortcut might work. So let's take a look at our final answer in this problem and ask, how many t's did we end up with and how many w's did we end up with? Well, on the outside of the radical, we ended up with 2 factors of t and 1 factor of w. On the inside of the radical, we ended up with 2 factors of t and no factors of w. And here's the key. How could we have known that up front? Well, we might have known that up front because what we're doing when we're looking for groups of 3 is we're really dividing the number of factors of t and w that we started with by 3, taking the whole quotient and bringing that number of t's and w's to the outside, and the remainder have to stay underneath. So that's really what we were doing. We were really doing a process where we started with 8 t's, and then it became 2 outside and 2 inside. So the quotient, when we divide 8 by 3, was 2 with a remainder of 2. In other words, if I divide 8 by 3, I get 2 2/3. Likewise with the w's. If I divide 3, the original number of w's, by 3, I'll get 1 with a remainder of 0. So I had 1 w on the outside and no w's on the inside. So the shortcut for how to take a radical or a root of a power of a variable is to divide the exponents. Specifically, divide the exponent by the index of the root. Whatever you get for your quotient, your whole number quotient, that's how many of those factors come to the outside of the radical. Whatever you end up with for a remainder, that's how many you keep underneath the radical. So let's look at one more example just to illustrate how this shortcut might work. Suppose I gave you the radical expression, the 4th root of x to the 9th, y to the 8th, z to the 15th. How are we going to simplify this? Well, let's use this shortcut. We have a bunch of powers, x, y, and z, each have exponents on them underneath the radical. So let's use the shortcut by dividing the exponent by the index of the root. So how many x's am I going to have and where are they going to be located? Well, let's divide 9 by 4 using this little long division notation. 9 divided by 4 is 2 with a remainder of 1, right? 9/4 is 2 1/4. Likewise with the y's. 8 divided by 4, well, that's 2 with a remainder of 0. So 2 0/4 is what you get when you divide 8 by 4. And finally, 15 for the z's. If I divide 15 by 4, I'll get 3 with a remainder of 3. So 15/4 is 3 3/4. And now that I know what the quotients and remainders are of these exponents, when I divide them by 4, now I know how to do this. All of the whole number quotients are going to tell me how many factors of x, y, and z end up making it to the outside of this radical. Specifically, 2 powers of x, 2 powers of y, and 3 powers of z. The remainders in those division problems then tell me how many x's, y's, and z's are on the inside that are left over. I have 1 x left over, I have no y's left over, and I have 3 z's left over on the inside of my radical. So when I simplify this expression, I get x squared y squared z to the 3rd times the 4th root of x to the 1st times y to the 0 times z to the 3. Simplifying that just by getting rid of the 1 exponent down the x, getting rid of y to the 0 and making it disappear, because that's what happens to factors raised to the 0 power, they become 1. We end up with x squared y squared z to the 3rd times the 4th root of x times z to the 3rd. So to simplify a higher radical expression, if that expression has a coefficient like the 40 in our problem, we have to implement exactly the same strategy we did when we simplified the square root of a number before. But then if there are also powers of variables underneath the radical, the shortcut for what to do with those is to divide their exponents by the index of the radical, take the whole number quotient and take that many powers to the outside, and leave the remainder number of powers on the inside.